Welcome to Qt e-Learning channel. In this lecture, we will discuss the stress relaxation cracking, reheat cracking. Description of damage. Cracking of a metal due to stress relaxation via grain boundary strain. In the creep temperature range during PWHT or in service at elevated temperatures. The temperature above which it occurs depends on the type of alloy. It is most often observed in heavy wall sections at various times and in various situations. Stress relaxation cracking has also been called reheat cracking, stress relief cracking, creep embrittlement, low creep ductility cracking, stress-induced cracking, and stress-assisted grain boundary oxidation cracking. Affected materials. Chromium molybdenum steels, especially 2,1/4 chromium, 1 molybdenum, steel with vanadium added, 2,1/4 chromium, 1/2 molybdenum, and 1/1/4 chromium, 1/2 molybdenum. Types 304H, 316H, 321, and 347 stainless steel. Nickel-based alloys, particularly alloy 800H, 800HT, alloy 617, and centrifugally cast 22 chromium 35 nickel niobium, used for heavy wall piping and headers in hydrogen reformer heaters. High-strength low-alloy steels are very susceptible. Critical factors. In addition to exposure to elevated temperature in the creep range, important parameters include the type of material, chemical composition, impurity elements, grain size, weld metal, and base metal strength, residual stresses from fabrication, cold working, welding, section thickness, which controls restraint and stress state, notches and stress concentrators, and welding and heat treating applied. Stress relaxation cracking occurs at elevated temperatures, when creep ductility is insufficient to accommodate the strains required for the relief of applied or residual stresses. Stress relaxation cracking can either occur during post-wet heat treatment or in service at high temperature. Stress relaxation cracking is normally more prevalent where large grain size exists, particularly in the low-alloy steels. For example, in the coarse-grained heat-affected zone. The approximate temperatures above which, or ranges within which, stress relaxation cracking occurs for different types of alloys are as follows. 2,1/4 chromium, 1 molybdenum vanadium, 840 degrees Fahrenheit. 1 chromium, 1/2 molybdenum, and 1/1/4 chromium, 1/2 molybdenum, 900 degrees Fahrenheit. Types 347, 321, and 304H stainless steel, 930 degrees Fahrenheit to 1380 degrees Fahrenheit. Nickel-based alloys, 930 degrees Fahrenheit to 1380 degrees Fahrenheit. Stress relief and stabilization heat treatment, of types 321 and 347 stainless steel. For maximizing chloride stress corrosion cracking and/or polythionic acid stress corrosion cracking, resistance can cause stress relaxation cracking problems, particularly in thicker sections. In the first half of 2008, numerous cases of stress relaxation cracking, primarily referred to as reheat cracking, occurred during 2,1/4 chromium, 1 molybdenum vanadium reactor fabrication. The cracks were in weld metal only, transverse to the welding direction, and in only submerged arc welding welds. It was traced to a contaminant in the welding flux. Affected units or equipment: catalytic reformer and FCC units, hydrogen manufacturing units, high-pressure steam piping, hydroprocessing. Appearance or morphology of damage. Stress relaxation cracking is intergranular and can be surface breaking or embedded depending on the state of stress and geometry. It is most frequently observed in coarse-grained sections of a weld has. However, it can also occur in weld deposits, as illustrated in figures. Crack at weld from type 321 stainless steel elbow, and cross-section through the weldment showing the crack, as illustrated in figures. Photomicrographs of the weldment area. For cross-section through the weldment showing the crack. Prevention, mitigation. Joints and nozzles in 1 chromium, 1/2 molybdenum and 1/1/4 chromium, 1/2 molybdenum, vessels and piping. Especially heavy wall sections, should be designed to minimize stress concentration as well as restraint during welding and post-wet heat treatment. Adequate preheat must also be applied. In design and fabrication, it is advisable to avoid sharp changes in cross-section, such as short radius fillets or undercuts, that can give rise to stress concentrations. Low heat input welding procedures help minimize grain coarsening in the heat-affected zone. Heating rates at temperatures above 480 degrees Fahrenheit should generally comply with the limits provided by ASME Section 8 for post-wet heat treatment. Metallurgical notches arising from the welding operation are frequently the cause of cracking at the boundary between the weld and the heat-affected zone. For 1 chromium, 1/2 molybdenum, and 1/1/4 chromium, 1/2 molybdenum. Vessels operating above 900 degrees Fahrenheit, follow the material grade, and post-weld heat treatment temperature guidelines in API 934E. For 2/1/4 chromium, 1 molybdenum vanadium welds, consider the recommendations for welding material screening tests in API 934A. For thick wall type 321 or 347 stainless steel piping, consider the possibility of stress relaxation cracking in deciding whether to post-weld heat treatment. Inspection and monitoring. For chromium molybdenum steels, surface cracks can be detected with WFMT, MT, or PT. For type 321 and 347 stainless steel as well as the nickel-based alloys, PT or angle beam UT, SWUT or PAUT, examination, can be used to detect cracks. Special procedures, equipment, and interpretation are often required for angle beam UT inspection of austenitic materials with a thickness greater than 3/4 inches, 19 mm, compared to similar thickness non-austenitic materials. Embedded cracks can only be found by UT examination. Inspection for cracking in 2/1/4 chromium, 1 molybdenum vanadium reactors during fabrication is typically done with TOFD and/or angle beam UT, SWUT or PAUT, with the demonstration block having defects as small as 3 mm side drilled holes, as described in API 934A. Related mechanism to stress relaxation cracking, reheat cracking, is creep and stress rupture. Stress relaxation cracking has also been referred to as reheat cracking, stress relief cracking, creep embrittlement, low creep ductility cracking, stress-induced cracking, and stress-assisted grain boundary oxidation cracking. Summary. Description. Reheat cracking due to stress relaxation during post-weld heat treatment at or in service at elevated temperatures. Reheat cracking more likely to occur in thicker sections and higher strength materials. Reheat cracking is intergranular. Temperature range. During PWHT or in service at elevated temperature. In the creep range. Affected metallurgy. Low alloy steels as well as 300 series stainless steel and nickel base alloys. Prevention. Designed to minimize restraint. Avoid sharp changes in cross-section. Using low heat input welding procedures. Inspection methods. WFMT, MT, or PT examination of carbon and low alloy steels. PT or angle beam UT, SWUT or PAUT, examination of 300 series stainless steel and nickel base alloys. Inspection for reheat cracking in 2/1/4 chromium, 1 molybdenum vanadium reactors. During fabrication is typically done with TOFD and/or angle beam UT, SWUT or PAUT. Practice time. Question number 1. A metal cracks because of stress relaxation during post-weld heat treatment of heavy wall section that is operating at elevating temperature. This type of crack is best categorized as answer is A. Question number 2. Which of the following statements about stress relaxation cracking, reheat cracking, is correct? Question number 3. What is other name for reheating cracking? Answer is D. This lecture is prepared by Samir Saad and this is his profile. Thanks a lot for watching and please waiting us for the next lecture.